In example 1, we want to determine our output voltage as the difference of our two input voltages, V1 and V2, using a differencing operational amplifier as shown below. What we see is we have a voltage source, VA, that's connected to a 10 kilo ohm resistor that then is connected to our inverting terminal of our operational amplifier at node A. Likewise, we have a voltage source, VB, that's connected to a 10 kilo ohm resistor that is then connected to our non-inverting terminal of our operational amplifier at node B. Between node A and our output terminal, we have a 30 kilo ohm resistor, whereas between node B and our output terminal, we have a 30 kilo ohm resistor and 50 kilo ohm resistor, which are separated by ground. To begin, we'll apply the assumptions of our ideal operational amplifier. That is, V1 and V2, i.e. the voltage potentials that are inverting and non-inverting terminals are equal, and I1 is equivalent to I2, which are both identically equal to 0. For us to construct a relation between our input and output voltage, we recognize that we have two nodes that each have a unique input voltage. That is, we will have to construct two KCL equations, one at node A and one at node B. Beginning at node A, we see we have I3 entering and we have I1 and I4 exiting. Recognizing that I1 is equal to 0 from our ideal operational amplifier assumption, we would have the following expressed in terms of Ohm's law. I3, which is VA minus V1 per 10 kilo ohms, is equal to I4, which is equal to V1 minus Vout per 30 kilo ohms. Or our output voltage is equal to 4V1 minus 3VA. Currently, we have V1, which is unknown. To determine V1, we'll apply KCL at B, such that we have an expression for V2. When we apply KCL at node B, we have I5 entering and I6 and I2 exiting, where I2 is equal to 0. Thus, I5 is equal to I6. I5, using Ohm's law, can be expressed as VB minus V2, which is identically equal to V1, per 10 kilo ohms, and this is equal to I6, which can be expressed as V2 minus ground per 30 kilo ohms, where V2 can be expressed as V1. Thus, V1 is equal to 3/4 VB. Now we can substitute this into our output voltage expression, where our output voltage was equal to 4V1 minus 3VA. Or our output voltage would be 4 times the quantity 3/4 VB minus 3VA, which is equal to 3VB minus VA. That is, our output voltage is equal to the difference of our input voltages by some gain, where our gain is expressed as a value of 3.